Hey everyone, my name is Ted Lutkus, and today I'm going to be talking about my C++ project. For my project, I was actually working with some physical hardware, and I decided to write some embedded C++ code that would be controlling the electrical components of this hardware. So what you're looking at right now is essentially a fluidic loop where if we're following my cursor, water is entering through this tube. It goes into this red bladder here. It's then pushed out by a paddle that's connected to this servo motor. If I can zoom in a little bit there. So you can see the fluid comes into this bladder. It's pushed by this paddle here connected to servo via some gearing, and it exits the bladder out this end, passes through this blue chamber, and then continues on to the rest of the system and eventually makes its way back up to this fluid reservoir up here. So in this system, we're measuring pressure across this blue chamber via two pressure sensors. These are just sensors from SparkFun, and they're measuring the pressure before and after the chamber to get essentially the change in pressure or the pressure gradient across the chamber. And by having these sensors and the servo motor, we can actually have essentially a feedback loop where we measure the system's pressure at any given point in time sent to this Arduino, which has our C++ code embedded on it. And given the pressure that we're reading and the pressure that we would like the system to be at, we can send a command to the servo motor that will adjust essentially the way in which it's pressing against the bladder to try and get closer to the ideal system pressure we want to be at. So I'm going to essentially show a video that just sort of demos, I guess, the bladder moving, so you can see that. So here what you're looking at is the servo actuating, and the piston is pressing against the bladder. And because of this displacement, it's pumping fluid out via the exit port here. Let's see if there's anything more. No. In terms of the stuff that the features that I've used for this project, it's mainly surrounding the embedded system element here. So that involves using essentially this embedded system and physical components. We need different ways to communicate with the components. For the case of the pressure sensors, we're using something called I2C communication, which, if I zoom in on the electrical bits here, so the sensors actually basically send an analog signal to our Arduino, and they're actually sharing the same electrical wiring, which is what's so great about the I2C system, is that we can kind of bundle up a bunch of different sensors so long as they have different addresses, and we can read them from the same essentially two ports on our Arduino. So that's I2C communication. It's one of my advanced features. And the other advanced feature is serial communication. So this is essentially writing bytes to a serial port. In this case, the serial port reading and writing that we do is writing to the servo motor via serial commands, and then reading from the Arduino via serial commands to a computer to collect data. So this is in the Arduino IDE, and this is the code that's essentially flashed onto that Arduino. You'll notice that there's some global variables here. There's some different conventions that take place when you're writing embedded code, and your scripts are generally pretty small. So it's actually okay here, and it's just one of the quirks of the Arduino system in this case. But importantly here, so we can see essentially the I2C device is starting up. So we're resetting and starting our two pressure sensors with the I2C communication. And then we can also see an example of writing to the servo motor and sending commands there via the serial port. And then also essentially some data collection that's happening in these two places, where we're taking the time, servo position, and the pressure readings, and we're printing that out to computers so that we can essentially see if the system's behaving properly. So now that we've gone over the two features that I'm using, I'm going to talk a little bit more about the control system that I set up. So this is so the controller is how I've sort of integrated some of the classing and inheritance into my project. So there's essentially a parent controller class, and the idea is that you could write your own control algorithms or extend beyond this class. And so long as you implement this functionality, your controller is going to be able to interface with my system and control it. I've just implemented two examples, one being the PID controller and the second being an LQR controller, which are just two different control algorithms. For demonstrating my project, I use the PID controller, and so I can describe a little bit more what's happening here. So with the PID controller, it's basically, if we go in here, we can see us actually calculating how this controller works in this bit here. The PID, without going into too much detail, it essentially takes the error that's in your system and you combine the essentially just a proportional gain multiplied by this error, a integral gain, which is I, multiplied by the integral of the error, and then you take the derivative of the error and you multiply that by a third gain, d. And if you choose these p, I, and d values properly for your system, and then you essentially add up those components, you'll actually get a control action that is optimal for your system and will allow it to follow desired behavior. Now, how do you choose these p, I, and d values? So that's actually commonly done in MATLAB. So this is a block diagram of the system. It might seem like there's a lot going on here, but I promise it's not too much. So I've sort of labeled these signals in here, and a block diagram is a way that you can kind of show a physical system using a mathematical model, and you can control or essentially tune a controller. So we have an input here, which is just a reference signal. In this case, we have essentially just part of a sine wave that's saturated at a value that's going into our system. And then we're comparing that with pressure that's actually coming out of the system. And I'm modeling the sensor dynamics here. So we're comparing what we want for the system to do versus what's actually happening. And if you subtract one from the other, that gives you the error of the system. The error is passed into the PID controller, which if I double click on this, we can actually see the gains, and those gains were collected just by tuning the controller here. So it does what my code does and basically outputs a theta, or an angle that we want the servo motor to follow. So that goes into our mathematical model of the system, which I've done on paper and put into Simulink here. And we can see the output of the or our results of tuning the controller in simulation. So the blue is just a desired tracking behavior that we want to follow, and the yellow is the system actually responding in simulation. So this is essentially with the PID controller in there, how our system should in theory respond given this input. So this is really good because now we can take essentially any desired pressure that we want, going back to our image here. We can essentially send a desired pressure that we want into the system, and leveraging the sensors and the servo motor, our controller, the Arduino, is actually going to essentially just modulate we're able to kind of directly control the pressure across this chamber, which is the whole goal of this project. So I'm going to essentially, after I know I've talked a lot about like some of this theoretical stuff and whatnot, but the result of all that is that, so we had this, essentially this desired curve that we wanted to follow, and this is the actual output from our system. You can ignore some of these labels here. The important bit is that we're able to actually follow a desired pressure curve, which is pretty awesome, and it's pretty rewarding given essentially just writing up this controller and leveraging some of MATLAB to implement that. So that sort of sums up what my project was and the features that I used for this project, as well as some of the classes that I've set up to control the project. And thank you for listening.